Let's analyze the titration curve. It appears that there are two equivalence points. One here, perhaps at pH 4.5, and one here, perhaps at pH 9. So let me draw I'm trying to draw a perpendicular at pH 9, and I'm trying to draw a perpendicular at, we'll just call it pH 5. Why I think this is a diprotic acid? Because we can see that to reach the first equivalence point requires 25 milliliters. To reach the second equivalence point requires 50 milliliters. So the other alternative is that rather than this being the titration of a diprotic acid, this could be a mixture of two acids, one with an equivalence point at pH 5 and one with an equivalence point at pH 9. The reason I believe this is a titration of a diprotic acid is that it requires another, to reach the first equivalence point requires 25 milliliters, and another 25 milliliters are required, an additional 25 milliliters are required to reach the second equivalence point. So these mathematics suggest strongly that this is a titration of a diprotic acid. That the key for a diprotic acid is that the volume to remove each hydrogen is the same. So you're not necessarily at twice the pH. We're not comparing the pHs, we're comparing the volumes. We have the equation of the titration, or the reaction between a weak acid, I just picked acetic acid, and the hydroxide. So I didn't even bother including the sodium ion, it's just a spectator ion. So as we're adding more hydroxide, more and more acetate ion is being formed. Now remember that let's analyze another titration curve. As we examine this titration curve, it appears that there are two equivalence points. One at about pH 4 and one at pH 10. The question is this the titration curve of a diprotic acid, one which has an acid which has two acidic hydrogens, or is this a mixture of two acids, one with an equivalence point at pH 4 and one with an equivalence point at pH 9 or 10, excuse me. What we notice is that to reach the equivalence point at pH 5 requires 25 mils of sodium hydroxide, and to reach the equivalence point at pH 10 requires 50 mils of sodium hydroxide. This strongly suggests that this is the titration of a diprotic acid, because the same volume of sodium hydroxide is required to reach the first equivalence, and an additional 25 mils is required to reach the second equivalence point. Let's examine the reactions. So we have carbonic acid, say with a pH of 2. We are titrating with sodium hydroxide. I'm just writing the hydroxide ion. The sodium ion is just a spectator ion. That means sodium hydroxide is in the burette. One of these hydrogen ions will be abstracted and react with the hydroxide to form water, so that we have the hydrogen carbonate ion, also known as the bicarbonate ion, and water formed. Now we can see that the bicarbonate ion also has a hydrogen which it can react, which it can lose. So let's write that equation. To interpret this is that carbonic acid loses the first hydrogen, requires 25 milliliters, and for the bicarbonate to lose the second hydrogen, requires another 25 mils, for a total of 50 mils to perform this titration. Thank you for watching. See you in class.